You're listening to the Common Descent Podcast.
Hello, David.
Hello, Will.
And hello, audience. Welcome to episode 151 of the Common Descent Podcast.
Sure like that number.
Yeah. We like to talk about all different kinds of paleo and Earth history topics here on the podcast. Today we will be looking at tails.
Tails, they're right behind you.
Yep. Tails, a body part that I feel oft gets mentioned but not focused on. Here we're going to focus on what is a tail and what are all the insanely weird things life has done with tails, and what can we learn from those tails?
Yeah, well, how have they diversified over time? What does evolution do with a tail? And then what do we as scientists do with a tail?
This topic, as all our topics are, was requested. We got requests from Brad, Susan, and Skittles to talk about tails.
Thanks.
And we will happily do so, because tails are super cool.
We're going to have a good time.
But before we jump into talking about tails, some announcements. Up first, as always, we have a Patreon, where you can get all sorts of extra goodies, extra content, extra audio, extra access to us.
Extra me.
And if you sign up at a certain level, we like to shout your names out here on the podcast. So welcome our new patrons, Stuart, Benjamin, David, Eric, and Sam.
Welcome.
Thanks so much for your support.
Thanks, as always, to all of our patrons for supporting our science educational endeavors.
Indeed, the Patreon keeps us running top to bottom. If you'd like to support us other ways, you can always just join the social medias, but we also have a Zazzle merch store. And now we are also part of the Audible Creators Program, so if you use our link, you can get a 30-day free trial with Audible, the audiobook site that has all sorts of books that you can listen to, download, or just stream. And if you use our link, audibletrial.com/commondescent, you can get that trial and support us.
It's a pretty cool deal. I want to give a shout out to Riley Black's latest book, which I also did in the last episode. It's super fun. Its full title is The Last Days of the Dinosaurs, An Asteroid, Extinction, and the Beginning of Our World.
Cool.
Riley paints a really cool picture of the ancient world before, during, and after the events of the end Cretaceous mass extinction. And it's on Audible, so that is our official Common Descent recommendation. Go check out Riley's book, and if you use audibletrial.com/commondescent, you support us along the way. So thanks in advance.
As for other announcements, speaking of past and upcoming events, we are at the end of October now, which means we've just wrapped up all of Spooky. Speculative Evolution is now done for 2022.
And boy, did we evolve some cool monsters.
Yes, this year was Monsters of Dungeons and Dragons. We did the Owlbear, the Displacer Beast, the Beholder, and the Mimic. And if you want to see how we evolved them into a semi-real world animal, go take a listen.
Yeah, and hop on our social media and our Discord, links in the episode description, to join the discussion with other listeners in our listening community.
Since we are at the end of October, we are also coming up on November and the end of the year, which means our end of the year Q&A is right around the corner.
Yes, we will be putting up the question submission form on November 15th. Once it's up, we will share the link to it on all the social medias. It'll be on Discord. It'll be in the episode descriptions. So keep your eyes out for that. You will be able to send in questions for us to answer. We will probably spend a few hours answering questions for the end of the year Q&A like we have the last few years. It's always a ton of fun. We love getting questions from people.
Yeah, so think up your questions, think of the things you want to hear us talk about, and keep an eye out for that questionnaire. And with that, we'll wrap up announcements, move on to our first section. Every episode, we like to gather up some recent paleontological evolution and Earth history news from recent studies and share them all with you. David, start us off with some news.
Well, since we're talking about tails, my first bit of news involves animals that had tails.
Oh, okay.
Yeah, we're not going to talk about their tails,
but we're on the right page.
They did have them. This is a bunch of late Permian mammal cousins that died in a drought.
Sad.
Yeah, this is research by Roger Smith et al. in the journal that we just call P3 because it saves us from having to say paleogeography, paleoclimatology, paleoecology, which is just too long a title. And in the blog post associated with this episode, link in the episode description, we will have news links. This one will link to an article in Live Science by Stephanie Pappas. The fossils in this study come from the Karoo sandstones of South Africa. This is a famous region for fossil finds. The fossils are about 252 million years old, right at the end of the Permian period. So this is right before the Permian mass extinction, the worst mass extinction that we have on record, right before the age of reptiles set in. This is a time period associated with mass extinctions, also major climatic changes, lots of volcanic activity and the Siberian traps. This research is particularly focused on looking at fossils of Lystrosaurus, which is a very famous mammal cousin. Early mammal relatives, we talked about these back in episode 47. Lystrosaurus is famous for having done really well around this time. The mass extinction happened and Lystrosaurus went all over the continent because apparently they were surviving really well while everything else was having a hard time.
Just the rats of that time, I guess.
Yes. The article describes them as pig-sized and quotes one of the authors describing them as a bit like a bulldog with a beak and some tusks.
Yeah. These have those little downward-facing tusks on either side of their mouth that you'll see pictures of these early, and they have like little bulldog squat legs. Real weird, but super cute.
Yeah, real cool animals. Excavation in this area found, the authors report, 170 fossils of tetrapods, so that's land-living vertebrates, mammal, reptile, amphibian relatives, all within about 2 meters of sandstone. Included among them were many Lystrosaurus fossils, often articulated, so the skeleton is relatively intact, in multiple clusters. So up to 8 skeletons of Lystrosaurus would be found in each cluster throughout this period of geologic sediment. This clustering, plus features of the geology in the area, leads the authors to suggest that the animals might have been perishing in repeated droughts.
Gotcha.
And the evidence that they have for this is as follows. For one, the fact that they're clustered together. The authors point out that this is something we'll see in animals today during droughts and stuff. You'll get animals congregating around the areas where they're trying to find the last available amounts of water or vegetation, but they'll all end up coming to one place, and then if there isn't enough water or vegetation, they all die there together.
Yeah, they all follow the same clues to a hopeful oasis.
Yes, and then they don't find it. Also, they looked at the histology of the bones in the fossils, so the growth patterns within the bone, and found that all of the Lystrosaurus were either juvenile, so not yet adults, or very young adults, which suggests that they might not have been living very long, possibly because there were difficult conditions to try to survive in. They also found that 2 of the fossils had skin impressions associated with them, and skin is rarely preserved alongside fossils. Oftentimes when it is, it's attributed to the carcass drying out very quickly, desiccating. That's not the only possibility, but that's often something that's associated with those. And if these were desiccated, dried out fossils, that also fits the narrative of a drought happening at that time, a very dry time period. So all this together, they interpret these fossil deposits as successive periods of drought that repeatedly over the course of, months, years, and so on, there would be droughts and animals would end up dying in this region in clusters.
Yeah, and we see that in our climates today where you have dry seasons that are just going to be particularly harsh with very little rain, and many areas experience seasonal droughts.
Yep.
That just take out a bunch of individuals.
So this is something that can still happen today, but in this study, it's particularly interesting that it's happening at the end of the Permian. This is a time period where evidence suggests the Earth was going through particularly high temperatures and lots of aridity, dry climates. Part of this was because of the supercontinent of Pangaea. We talked about this back in episode 141, the central area, a lot of the land mass of Pangaea seems to have been very dry, very arid.
Just too far for clouds to make it.
But also, the volcanic activity going on over in Siberia was releasing lots of greenhouse gases that were raising the temperatures. So this was a particularly warm, dry time. And one of the authors makes the point in the article that what might have been happening at the time is that overall warming of the climate was increasing the likelihood of extreme climate events. That severe drought might have become more common in a time where it was particularly warm and particularly arid, which is one of those sentences that's very memorable to read, both because A, it tells us something about ecosystems and changing and extinctions in the past, but also because a globally warming climate increasing the likelihood of extreme weather and climate events hits real close to home these days.
Yeah, we've heard that a number of times.
Yes, so a valuable time period to research for multiple reasons.
Well, and it's also interesting that you can find patterns of death in certain events, certain climactic or just seasonal events, weather events. Not only that there is patterns of dying, that storms are going to increase deaths, droughts, floods, but that there is a particular pattern to the way things die.
Yeah, drought leaves a certain signature of death in its wake.
Absolutely. Just like if we find bodies that are piled up together, that's often a sign of a flooding event that washed all these animals to the same spot and then left them there. I didn't think about a drought significant one until you mentioned it, and then it's like, oh yeah, no, because you're desperate to find things.
Yeah, that one remaining watering hole in the region is going to attract all the animals that can come to it.
Because everyone is desperate.
Yes.
Everyone is on the same page of just trying to survive. And it also makes sense that young ones might be found more often because young are not as hardy as adults when it comes to things like droughts and famines.
Yeah. Or possibly that they are more hardy, so they make it all the way to that watering hole, and then that's where they starve because there's not enough material, there's not enough food and such.
Also true.
I don't think the authors attribute it one way or the other, but that was the thought that came to my mind.
Yeah, I know I've seen in documentaries lots of times of young getting left behind just because their little bodies can't handle it.
Yeah,
that's where my mind went to.
Yeah, could be either one.
And yeah, that's an interesting pattern to note.
Yeah, poor little guys.
Yeah, sad. But once again, tragedy makes good paleontology. Well, my next two bits of newses.
What?
Because I'm going to do them back to back because they deal with the same sort of stuff.
All right. We're mixing it up. Oh, long-time listeners are not going to know what to do.
What's happening? When does he stop talking?
Will's going to talk forever.
Never. Both of these news pieces deal with early jawed vertebrate fossils, aka jawed fish, some new finds that give us insights into early jaws and pushes the date back a bit, as well as having to do with limb development.
Oh, hey, that's topical.
Yeah, it is. The first research is by Yuanju et al. In Nature, and the article is by Riley Black in Smithsonian Mag.
And we've talked about her recently.
Hey, Riley! This study is in response to the discovery of a new Lagerstätten.
Ooh.
These are fossil sites that we've mentioned many times before that are noted for unusually good preservation of fossils.
Yeah, places like the Burgess Shale or the Messel Pits.
These are sites where you tend to find lots of articulated, full body, all in one piece fossils. Soft tissue very often is found at sites like this. Just the best fossil sites you could ask for, typically.
Yes.
This new site is found in Chongqing, South China, and is a Silurian site, so it's 436 million years old. Now, this is important for our conversation of jawed vertebrates. So jaws, your opening and closing mouth, evolved first in fish, and our fossil record for complete jawed vertebrates goes back to the late Silurian, about 425 million years old. But molecular evidence, when we look at the rate of mutation and evolution and estimate how long ago that should have happened, gives us an estimate of 450 million years ago at the end of the Ordovician, the period before the Silurian. And there are some fragmentary fossils at the end of the Ordovician that seems like it might support that, but we don't have good fossils between those two dates. So we've got a gap, a 25 million year gap, where we're unsure of what's happening with Jaws during that time, even though we expect stuff should have been happening.
Mm-hmm.
This fossil site falls in that gap.
Oh boy.
And it falls nicely in the middle, so it pushes our date back a bit, and we do have jawed vertebrates here. Now, there's lots of cool specimens here. One of the news articles called it an aquarium's worth of early vertebrates.
Oh, cool.
Which is such
a great description.
Right? Nailed it. They said that there's just tons of very diverse fossil organisms, early fish here, well preserved with complete bodies, some with jaws, many without jaws. This includes things like some of the earliest relatives of sharks. One of the best preserved specimens of a jawless group of fish called the Galeaspids. This species is Tuja aspis vividus and was described as basically a Roomba with a tail. It was one of the armored fish that had that armored faceplate up front and then a fleshy tail behind it. The bones had been found and the head shield were known for this group long before this site, but this specimen preserves the soft tissue of the tail now.
Oh.
So we have a more complete image of it, and this includes some of the earliest fish with paired appendages, paired limb-like structures.
Yeah, because early vertebrates looked kind of eel-like.
Yes.
Without proper fins, they just had sort of sea snake-like bodies that they would wiggle through the water.
And we'll talk more about that on my second news.
And also later in this episode.
Indeed.
Spoilers.
Now, the fact that this is a Lagerstadt may be part of the reason we had that gap, is that a lot of these specimens are very small and very delicate. So it may be that the early history of jawed evolution needed a Lagerstätten to be preserved.
Right, that kind of animal is just too unlikely to preserve under typical fossilizing circumstances. An exceptional fossil site is what you need to see them at all.
Yeah, so we may have to look for more Lagerstätten from this time gap to see if we can find more evidence of early jaws. Now, they do not make any major claims about jaw evolution here, but they note a number of specimens which push this date of jawed vertebrates back and are going to be notable for future studies because a lot of these are new species.
Cool. And these are the earliest examples we now have.
Yes.
Of jawed fish, which always cool to extend the timeline of something, but also it means for any researchers out there who were interested in that question, now they can plan their trip to go check out these fossils.
Absolutely. And some of these also are weird, so they will likely be informative for their groups just in general. The most common specimen at this site was a placoderm, one of the armored fish, the famous early jawed fish.
Episode 29.
Jujan osteus mirabilis was only like an inch long, so itty bitty.
Tiny fish.
Front half had armor, back half was more like a typical fishtail, and it combines characters from a number of major placoderm subgroups, so it likely will be informative for placoderm evolution. It also has some features that seem to, as they said, foreshadow the transition from the placoderm skull roof to a more bony fish condition. There was also an early chondrichthyon, which is the group that includes sharks and rays and their cousins.
Episode 48.
This one is named Xenacanthus vermiforme. This one also had bony plates, which was previously unknown in chondrichthyons.
Oh, cool. Like armor plates,
yes.
Like in the placoderms.
This one was around the shoulder area. I found one description. Said that they had like shoulder armor, it seemed, where the shoulders would be if they had shoulders.
Right, exactly.
And had a dorsal plate like in placoderms.
Oh, cool.
But the rest of the body plan was very chondrichthyon.
Very much like sharks and such.
Very much like that sharkish group.
So just a shark with body armor.
Basically.
Awesome.
I found one description that said it had a weak toothless jaws, so it's probably feeding on small, soft-bodied prey.
Mm-hmm.
So even some of these jawed ones did not yet have teeth. So we have a mixture of jaws as well.
Right, a variety of mouth types.
There was also another relative of chondrichthyons, which they named Fanjingshania renovata, which also had a mixture of characteristics, some seen only in bony fish. So your typical fishes that you think of, not in your shark cousins.
So we're just seeing this mosaic of early fish features.
Yes.
That would get dispersed among fish groups later on.
Precisely. And they made a note that as we often like to point out, early points in lineages is often very hard to tell ancestors apart because your features have not become distinct into bony fish, shark, and placoderm lineages. They also found teeth at the site. This is actually a separate paper, but it also noted another shark relative, which they called Chinodus duplicis, which does not have body fossils, but in another paper they described the teeth.
There were several papers that came out all about this fossil deposit.
Yeah, this fossil deposit made big news. Together, all of these push back the date for our knowledge of teeth and jaws in the vertebrate evolutionary record by a decent amount. And this is just the initial studies coming out about this site, so I'm sure there'll be tons more. One of those other things, going back to Two-jaw aspis, the little Roomba one that was jawless, so this is not dealing with jaws, but that complete specimen preserved the fins. What they found is that along the body walls, they had two continuous fins, basically kind of down the body, but symmetrical on both sides. So they had one on either side of the body, and these were kind of on the side toward the bottom. They called them ventrolateral fins. They also had 3 unpaired dorsal fins and a symmetrical tail fin.
They're just covered in fins.
The side fins are the ones that are most interesting to them because one of the other interesting things about early fish evolution is the evolution of paired appendages. This research is by Jukun Guy et al. In Nature, and the article is by Clyde Hughes in UPI.com. The reason they were so interested in this is because paired appendages, our left and right arm and our left and right leg,
very familiar,
evolved from the pectoral, the front fins of fish, and the pelvic, the back fins of fish, which are also paired left and right, left and right. So it's a very unique feature that ended up being very important for much of life later on.
Mm-hmm. Episode 77.
But the earliest fish did not have paired fins on the sides of their body like that. These paired long fin, continuous fins are likely the ancestral state.
Gotcha. I'm imagining, like, when you think of an eel, it has that one long fin along the top and one long fin along the bottom. I'm thinking that, but along the sides of the body.
Precisely. This is what's often called the finfold hypothesis, which is one of the potential suggested routes that paired limbs could have evolved. Basically, this long fin would eventually separate into the front pectoral fins and into the back pelvic fins later on in jawed vertebrates.
Mm-hmm.
So this is not something that happens with the jawless fish, but it will eventually happen later on down the line. This is some soft tissue preservation of those long fins, which were already had been hypothesized.
Yeah.
This seems to line up with that.
That's awesome. So we've got new insights into the evolution of early features. It's so cool because we often will talk about news where it's like, oh, insights into the early evolution of this feature or that feature in this group. But here we're talking about jaws and legs.
Yeah.
Like limbs as a concept. That's a very cool set of finds. It's always so cool. This has happened a number of times. We've talked about these on the podcast. When a new fossil locality is either discovered or finally starts getting some publications coming out of it, and you can tell that a star is being born.
Yes.
Like, this is going to be the subject of tons of studies into the future. Like when the famous southern China fossil sites with dinosaurs and birds and such started getting published on, or like the famous sites we've talked about, like the Burgess Shale or the Maison Creek, that at a certain point someone discovers what will end up being a world-famous, super important, extremely informative fossil locality.
Yeah, it's just referenced all the time. Yep.
So that's really cool to hear about, and I'm sure we will be talking about those fish in future news sections.
Surely.
Well, I've got one last bit of news for this news section, and it is a little bit different. This is research about paleontology in video games.
Hey!
It's awesome. This is a study by Thomas Clements et al. In EGU Sphere Geoscience Communications, and in the blog post, we will link to a press release from the University of Binghamton. I will probably also link to the paper itself because it's open access, it's relatively accessible, and it's really interesting, especially for anyone who's into science communication or just video games and dinosaurs and stuff.
And who's not into those three things?
Right. Video games are pretty popular. They're kind of a big deal. You might have heard about it.
Yeah, no, I mean, I've tried them.
The authors examine video games because, as they begin by explaining, video games often include scientific themes, scientific concepts, scientific ideas, scientific subjects, and when we think about people's exposure to scientific concepts, video games can be very influential. People play them for a long time. For kids, video games can sometimes often be some of their earliest science communication experiences, their earliest exposure to certain ideas.
It's very similar to the way many people have ideas from movies that have been just perpetuated.
Absolutely. But video games are not typically primarily educational. They're using these concepts to fill out the game, but they're not meant to be teaching with them. This study is a massive review of just how paleontology concepts show up in video games. They point that their goals are to highlight common misconceptions, common tropes, themes in video games with paleontology, to bring awareness to people who are interested in communicating science, that these are things they might encounter with audiences who play video games, or if they're trying to use video games for education, these are things to keep in mind. And they also point out that this paper, they hope, will bring awareness to game designers.
Yes.
Who might not be aware of some of these themes and concerns. The study focuses on commercial off-the-shelf games, and they specify not educational video games. Because those, of course, exist. They're not looking at those. They identified hundreds of what they called paleo-themed video games.
Yeah.
They said that as of 2021, there are 270 paleo-themed, off-the-shelf commercial games on Steam alone.
Yeah.
Just on Steam, which is the biggest online catalog of video games. In this paper, they didn't look at games that use paleontology stuff as just sort of the background.
Yeah.
They mentioned, like, sometimes there'll be just, like, a museum level in a game or a dinosaur skin for your character. They're not looking at that. They're looking at places where they're actually using paleontology concepts as part of the game.
All right, gotcha.
So they do two main things. One, they identify major categories of how paleontology shows up in games. And the categories they list are ancient animals as adversaries, when they're the bad guys. You're like Turok Dinosaur Hunter, where you're shooting dinosaurs. Ancient animals as tools. And they point out games like Ark. They say that probably the best known example of this is Yoshi in Mario Brothers. Games where fossils are collectible items, like Animal Crossing.
Yep.
Ancient animal management, like the Jurassic Park games where you build your own Jurassic Park zoo and you're managing the animals. And ancient animal simulators.
Yes.
Like Saurian, where you're playing as the dinosaur in an ancient ecosystem. And they talk about how each of these categories uses paleontology ideas, how educational, like what the potential is for educational concepts. And then they have a whole section on common tropes in paleo games. And they specify a trope is a recurring theme or motif. Typically, we use the word trope in a sort of a negative context to refer to something that's cliche or repetitive, but a trope just means something that happens over and over again. It doesn't have to be a negative thing. Like, the hero's journey is a trope.
Yeah.
It's a recurring theme or motif.
Yeah, it's just that it's just a useful tool. Sometimes it can be overused.
Absolutely.
But that doesn't inherently mean it's bad.
So they go through a whole bunch of different tropes. For example, they talk about, and they use the term, monsterification.
Yay!
Which is very exciting, because we use that term all the time. Making ancient animals into monsters. They talk about a lack of diversity, that dinosaurs and certain dinosaurs tend to be most popular. They talk about the ways paleontology info shows up in games, that it can be sometimes really informative, sometimes misleading. They talk about depictions of concepts like evolution, cloning extinct species, recurring themes like that. And they also, those are things that we will talk about a lot in our Silver Screen Science episodes, things like that. But they also go into a bit of detail on subjects like ethics in paleontology. And they talk about how a lot of video games that have fossils in them, the fossils are commodities to be sold or traded, which touches on ethical questions here in the real world. They point out the depiction of unethical scientists. They used an example, I think, from Red Dead Redemption of a paleontologist who they said it looks like is probably based on Mary Anning, but then is just a very unethical, bad scientist, which is sending very awkward mixed messages.
Weird.
It made me think of the paleontologist character from Pokemon Sword and Shield.
Oh, yeah.
Who, same sort of thing. And they highlight diversity issues. And they talk about depictions of paleontologists themselves in video games being predominantly older, white, able-bodied men. And they also highlight trends that are common across video games of racism or sexism or hypersexualization in some characters. So the whole paper is just this excellent review of looking at paleontological games from a science communication perspective and what topics to think about, what to keep in mind as science communicators in a world full of video games, or if you're thinking about using video games educationally, or if you're thinking of creating video games with some of these concepts in it. It's a super cool paper with lots of really cool discussion within.
Yeah, no, it just sounds like they took a look at dinosaurs in video games and paleontology in video games from every angle that you could.
Yes.
Which is really, really awesome. It's cool to see it as a study.
Yeah.
Like, it is an official published study. That's fantastic. And yes, that's a really, really cool dialogue to have. Like, that's a great way to look into the aspect of paleo science education and outreach. And I also think this is a great way, like you said, to bring awareness to a bunch of features that people just probably don't ever consider.
Yeah, well, most often, I would imagine when these things come up, it's in contexts like us, right?
Yep.
Talking about these tropes on the podcast, which is bringing awareness to it and discussing it. But this puts it in a referenceable paper.
Yes.
That now other research can build upon.
It's useful. It's usable.
Yeah, in a more wide and more academic context, which is very cool. Like I said in the blog post, I'll link the actual paper.
Yes.
Because it's really cool. Like I said, relatively accessible as far as academic papers go. So anyone who's interested, we'll link it there, and I encourage you to check it out.
Awesome. And with that, we can wrap up the news and get ready for our main discussion of tales.
Woo!
What tales are and what different groups have done with tales. What are the trends we see across animals and how their tales differ? After the break. I feel like tales are one of those features of life that though we are all aware of them, we don't think about.
Well, they're always behind you.
They're always,
where you never look.
They're always back there. Who knows what they're doing? Tales are super common.
Ubiquitous.
Yes, like
everywhere.
They are a feature among vertebrates.
Yeah.
Like, there are those of us who have lost them, which we will talk about.
Yes.
But in general, all vertebrates ancestrally had tails, and most still do.
Yeah, it's like arms and legs.
Yes.
So yeah, that's a thing that tetrapods have. Those who don't are the rare exceptions.
Exactly. So tails are just this extremely common feature of life, of animal life.
Mm-hmm.
And as is often the case when we're defining things here on the podcast, we all know what I mean when I say a tail. But let's talk about, like, anatomically what distinguishes the tail. Yeah. So the long, waggly thing behind the bodies of many animals.
Yep. That long extra part coming out the butt.
Yep. The thing that wags on dogs and twirls and flicks in cats. A tail is basically just the general definition, an elongation of the trunk, your body.
Yes.
It is an elongated part of the body. It's in line with the body, and it comes off of, especially in us vertebrates, us bony animals, the spine.
Yeah. In vertebrates, if you look at a skeleton, the spine just continues past the hips into the tail.
It is typically the portion that's behind the cloaca or anus.
Yes.
That is often the distinction. Wherever the butt is on the animal, everything behind that is tail.
Yeah. Which is why, to answer the question that is oft asked, snakes have a long body and a short tail, usually.
Yes.
Because the cloaca, and indeed the sacral vertebrae that mark where the tail vertebrae start, is way back on the body.
Yes, it's indeed toward the end of it. Tails are typically the same structure as the body, but they lack a body cavity. So they don't have a space inside for organs.
Yes.
They'll have muscles, they'll have bone, they'll have skin and nerves, but they don't have any of the digestive tract because it ended with the butt back there. They don't have like livers or kidney, like none of the organs make it into the tail in vertebrates. But there are other structures that are very similar to the animal tails we typically think of that are not vertebrate tails. Arthropods, invertebrates, often have tail-like structures. Things like the scorpion tail, whip scorpion tails, even thinking of like the abdomen of bees and wasps that are maneuverable, that they can wiggle those around and they can position them very much like many vertebrate tails can do. These, of course, are not the same structure.
Right. There's no spine in that.
There's no spine in that because these two lineages of life are so distantly related. These are different anatomical structures, but you will hear them called tails all the time.
Yeah.
Scorpion tails are referred to as the tail in research publications.
Yeah, that's basically what it is.
That's what that is called. But it is different. You will hear a couple of terms go around. Metasoma is the last portion of arthropods, so your exoskeleton creatures' bodies, that compose of three parts. So insects have their three body parts, the head, the thorax, and the abdomen. The metasoma is the last section of that abdomen.
Okay.
It is going to be that area. So
yeah, we talked in the insects episode 99, that even though insects' bodies have three main portions, those portions have sections to them within those sections.
Yes. In many groups, the metasoma is basically the same thing as the abdomen. Like, the head is often called the prosoma, the thorax is often called the mesosoma, the abdomen is often called the metasoma.
Okay.
So it depends on which usage you're sometimes hear, but last section, this is the big bulb on the end of an ant. This is where their guts and organs are.
Mm-hmm.
Their organs are at the back of their body. The part with the legs, where we would have most of our organs, is not where most of the breathing and digestive system of an ant or a bee or most insects is held. In a scorpion, this makes up the tail. This is the long bendy section, which means it also carries some of their digestive tract. The anus of a scorpion is actually on, if I remember right, the second to last section, the fourth section, if I remember correctly. So their anus is on the tail.
Oh, interesting.
Yes. They're very different from us vertebrate tails where there is no organs inside it.
Yeah.
These continue, it's just a continuation of the body. Some of them have turned it into a tail.
Yeah, and us vertebrates, the tail is a lot like a limb, like an
Yes.
arm or a leg. It's bone, it's muscle, it's tissue, but it's not organs.
Now, you will also see the term telson for invertebrates. This is the last section, the last bit
Gotcha.
of the metasoma. And in some, that's fairly unimpressive. Like, the scorpion tail is the metasoma, the stinger is the telson.
Right, the very last part.
That itty-bitty bit at the end. But in others, the telson is much more tail-like in the way we perceive it as vertebrates. This includes things in other chelicerates, the group that includes scorpions. Horseshoe crabs, that big long spike at the back of a horseshoe crab,
Oh, yeah.
is the telson, which is used very much like a tail. It uses it to flip itself over and to right itself when it gets rolled on its back. Things like whip scorpions and others of that group that have the long, thin flagellum at the back of the body, that is the telson. That is the last section of their back portion. This also includes the fan portion of a lobster tail. The fan on a lobster or a shrimp is the telson. The rest would be their abdomen, basically. What we call a lobster tail when you're eating is arguably not the tail, it's the back of the body, but that's also the case in the scorpion.
Right.
So us vertebrates, all tails come from the same source. They are all the same structure that have diversified. In arthropods, that is not the case. The tail-like structures you see are separately evolved. They're different parts of the animal. Some of it's just the end, some of it's most of the end. It depends on which group you look at. So you have a ton of diversity here when it comes to what actually you would consider a tail in arthropods, if you even actually want to call it a tail.
Yeah. So evolution in animals has just repeatedly hit upon that it is useful to have an elongated back part of the body.
Yeah, a behind you limb.
Yeah, and I guess it's worth mentioning briefly here that even in single cells, there will often be a structure you call the flagellum in the whip scorpions. Bacterial cells, in us humans, sperm cells.
Yep.
These are individual cells that have a tail, kind of, that is called the flagellum, that is usually used to propel them along when they're moving.
Precisely. Tail-like structures are extremely common. Now, through this episode, we will be focusing more on the vertebrate tail, since that is a singular evolutionary structure.
Right. And since we know a lot more about it.
Yes, and there's consistency. Like, we can compare them to one another. A scorpion tail is its own thing. It is unique. We've not seen a scorpion tail other than in scorpions.
Yeah.
So we can't compare it to other tails the same way, though there are sometimes it will come up. Now, this topic, like so many of the topics we cover here, is bigger than one episode, but tails are really big, much like when we did ants. There's so much diversity to tails. It's insane what animals have done with their tails through evolution. And that means that we are just going to touch on some of the big examples of this diversity. If you're thinking of your favorite tail, it is quite likely that might not make it into the episode.
I was going to say, listeners, think of your favorite examples of tails in nature and then see if they come up in the episode. And if they don't, send us a message and let us know what your favorite tails are.
As always, we'll be happy to hear about it. Now, one of the things we see as a very obvious signal of how diverse they are is just tail length. That's probably the easiest to just glance and be like, short tail, long tail, medium tail. Tail length is really diverse, and there are some major trends that are noticed with tail length. Some consistent times we see it involve in groups, behaviors it goes along with. Particularly mammals, this has been studied a bunch, because mammals have extremely variable lengths of their tails. From having very long tails to no tails, mammals have shrunk and lengthened their tails extraordinarily. You'll even see notable variation within a single species across their population. Like, tail length is very easy to adjust across mammals, it seems. Now, there are a few factors that have been pointed out as likely drivers of tail length that are some of the main selective forces. One is locomotion. Are you using your tail to get around, or are you getting around in a way that would help you to have a long or short tail?
Lots of animals, the tail is important in getting around, like animals that swim, like animals that move through trees, etc.
Exactly. This is also the case if you have a particular need for balance, like kangaroos use their tail as a counterbalance for their hopping. It acts as like a spring to counter the motion of the hopping.
Yeah. This is also the case in dinosaurs, for example, where the big long tail is a counterweight to the heavy front of the body.
Are you moving in a way that needs a tail? And long tails often help, but also short tails can come in handy if you're not needing something weighing you down in the back.
Yeah, if all you need to do is swat flies, you don't need a big long tail.
Exactly. Diet comes up because it is often used differently. Cheetahs use their tail like a rudder to help them steer while they're running. Bats use their tail to catch insects. So many predators will use their tail as a part of their predation. On the flip side, many prey items don't want to have a long tail.
Yes.
Because that's easier to grab.
Yes.
Rabbits and many rodents will have shortened tails that are either tucked or physically shorter because, you don't want to have some big long hanging thing that might be easier for the predator to get a hold of. We'll often see this, and very typically, it is a reduction of the vertebrae of the tail, a number of vertebrae.
Yeah, that's the way that the tail gradually evolves to be shorter.
Yes, that happens quite often. Another situation where tail length comes in that you might not expect is climate. We talked about this a bit in our gigantism and dwarfism episode.
144.
That we tend to see a trend of limbs getting longer or shorter or beefier or thinner based on how cold or warm your climate is.
Yeah, we might also have mentioned that in episode 114 about polar life.
Yes, I think we did. If you have a long tail, it can increase your heat loss. If you're trying to lose heat, you can radiate it off a long tail. Or if you're trying to conserve it and have less surface area to lose heat from, you can have a shorter tail.
Yeah, this is also we can see this in our own limbs.
Yep.
The reason that your fingers and toes are sometimes the first to get cold on a cold day is because they are far from the center of the body.
And they are thin, which means they have more surface area compared to the mass inside it.
Yes.
There's not a lot of meat inside your finger to keep it warm, but there's lots of area for heat to leave it. We'll also see animals that use their tails to combat the climate. Squirrels have been noted. There have been squirrels that have shown using their tail as a blanket to trap heat, wrap themselves in their tail, or as shade, as a parasol.
Huh.
Yeah.
I never thought about that.
So climate can affect, and if you don't need that, you'll have a short tail to just conserve, but if you want to lose heat or warm yourself, you might need a longer tail. So it comes in, these things all affect it. But by far the thing that studies have shown has the heaviest effect, the strongest trend with tail length is, as they put it, substrate use. What environment are you moving through?
Yeah.
Are you swimming? Are you digging? Are you climbing? Are you running? What part of the environment are you moving through? Because each of those have benefits or costs to the length of your tail. We already mentioned running animals will often have longer tails to help them steer. We see this in cats and dogs. Probably the most common one you'll see as an example is climbing animals. Arboreal tree-dwelling animals will have longer tails to balance themselves with, or to right themselves when they're in a jump or a fall.
Yeah. Or to physically hold on to something while you're up in the tree.
Precisely. It also goes the opposite direction. Subterranean animals, you don't have a need, and you also probably don't want a long tail if you're going through burrows. So you see things with moles and other diggers that have very, very short tails.
You mentioned that this is particularly common in mammals, but I have seen studies that have also shown that this is present to some degree in snakes.
Absolutely, yeah.
Similar trends.
And we'll see it in lizards. A climbing lizard often has a much longer tail versus one that's not going to be...
Yeah, and burrowing lizards will often have these little short tails. Not universally, but that is a trend you will see.
This is so strong that closely related species, one that is arboreal versus one that is terrestrial on the ground, will show notably different lengths in their tails.
Yeah.
It is more important where they're living than who they're related to.
And as we've talked about before, the kind of evolution that is involved in lengthening or shortening the tail seems to be a relatively simple step.
Yes.
We've talked about this with the necks of sauropods. We've talked about this with just the bodies of snakes. Adding or subtracting vertebrae, especially in a long, repetitive string of vertebrae, seems to be a relatively simple thing for evolution to do relatively quickly.
About as straightforward as copy and paste or delete.
Yes.
So tail length is really responsive to the lifestyle an animal has, but also very informative. If you see an animal with a long tail, you can immediately make some potentially accurate assumptions about that animal based off of what kind of tail they have.
Yeah, and we will often do that with fossil species.
All the time. Now, there is also the other extreme of having a long tail, which is not having a tail.
Just getting rid of it. And not animals that never had a tail in the first place.
Nope.
Never evolving one. But animals whose ancestors had tails and they said, you know what? Nah.
Which, and we'll get into more detail on this later, any vertebrate, meaning if you have bones, you ancestrally had a tail.
Yes.
At some point, your lineage had a tail.
Looking at you, frogs.
Yep. So all tailless vertebrates have to have lost their tail at some point.
Yeah.
Which may seem weird since we just went over how useful they are, but it has been linked with certain forms of mobility, like hopping, or it's even been connected with our upright gait, that a tail might not have been as important or may have gotten in the way of, that they may be connected to. The way we started moving made a tail unnecessary or less useful.
Mm-hmm.
But we're still not sure why and exactly how tail loss happens in all the groups it happens in.
Yeah, and considering that it has happened in frogs and birds and apes and other examples, it probably has been a slightly different circumstance in every one of those cases.
And sometimes very quick. In us humans, we actually don't know the full story of how our tail was lost because we have not a great fossil record for that period of human evolution because it happened really quickly. When you take a look at human ancestors, going back about 33 million years ago, our common ancestor during that time, the common ancestor of old world monkeys and what would lead to our tailless lineage, possessed long tails.
Mm-hmm.
Then, 15 to 20 million years later, the closest ancestors to us at those times have already completely lost their tails. So in 15 to 20 million years, our tails went away.
Yeah.
Which is pretty quick. Like that, evolutionarily speaking, that's pretty fast. So there had to be some decent selection to losing the tail, and we're not sure exactly what that transition looked like. We do not have a great record of those fossils. But we still do have remnants of our tail. We still do have a little bit of extra vertebrae at the end behind our hips. That is the vestigial human tail, which every now and then you will find conditions where it continues to grow in the early development and you get a human tail.
Yeah, because again, accidentally lengthening or shortening a tail seems to be pretty easy to do.
And it is very likely that we still have the genetic coding for a tail. It's just not active typically.
Right.
This happens very often with ancestral traits that sometimes will get turned on by mistake during development, and you will have a trait, an unusual trait come up that's not typically found in that species, but ancestrally might have been.
Yeah, so in humans and other apes, there is this remnant of the tail, this last remaining section. That's also true in birds. It is not, to my knowledge, true in frogs, where their spine stops at the hips, and then they have these long hips, and they're nothing past that.
Yep.
In adults, at least.
Yes, exactly. Because as tadpoles, they have little tails.
They have tails.
Now, we've already mentioned some of the many ways tails are used. I wanted to briefly just go over some of the really peculiar and interesting trends we see in tail usage. One having to do with mobility. We talked about swimming. They're important in flight, and steering for birds and bats and stuff.
Absolutely.
But there is a group that uses their tail to walk. Kangaroos have a long, powerful tail that we mentioned. Kangaroos and kangaroo rats, which are not related but hop in a similar way, use their tails as a metronome-like counterbalance to keep them stable while hopping. But large kangaroos, their back limbs are so oversized that it makes it difficult for them to walk normally when they're moving around slowly. Like they can't walk one step at a time, even though they're typically up on two legs. And they can't even walk on all fours normally. Their legs are disproportionately large compared to other mammals, so they will use their front limbs and their tail as a tripod, lift up the back legs while holding their weight on their hands and tail, move those forward, and then move the arms and tail forward for the next step. This is known as pentapedal locomotion, and it is only known from this group.
Cool.
And even more specialized, it is not known from many smaller cousins of kangaroos, wallabies and quokkas.
Oh yeah, this is a big kangaroo feature.
This seems to be true pedipedal locomotion, seems to really just be a big kangaroo thing. Many of the others will more just hop like rabbits, just a little hopping four-legged movement, or will drag the tail, but not ever support themselves with it. So they may be acting as a kind of a kickstand.
Right, it's for stability.
Yes. But not actually lifting any weight with it.
Yeah. I've heard it suggested that Tasmanian devils might also use their tails kind of that way as a to prop themselves up in certain situations. I think some extinct marsupials have been suggested to do something like that.
Absolutely. But this is a truly unique form of mobility.
Yeah, five-limbed motion in a vertebrate.
Yes, with the tail. Another form of mobility that you'll see, which we mentioned, which you alluded to, is prehensile tails.
Which is just one of the coolest things to do with a tail.
So prehensile means able to grasp. And a prehensile tail is one that has the musculature to wrap around branches or surfaces to help typically with climbing.
Yes. And that's an important distinction because it can be very easy to think, if you're thinking about cartoons and stuff, that all tails are able to wrap around stuff. We often picture tails as being very mobile.
Yes.
But most animal tails are not actually able to bend fully around something, and certainly not very able to grip that thing with any degree of strength.
Yeah, like a cat's tail can bend, and they are quite bendy.
Mm-hmm.
And they have muscle. That's why they can flip the tip versus the whole length. They have fairly good control over the entire motion of the tail. But, like, that cat can't grab something. Like,
you can't grab a cup and pick it up with the tail.
Yeah, they don't have a lot of musculature for affecting things with the tail.
A prehensile tail is the kind that writers give their superhero characters when they make them have tails.
Yes.
Is the kind of tail that you can pick up your coffee mug and bring it over to you.
Precisely.
Prehensile.
Now, you will see the terms prehensile and semi-prehensile. Typically, all that's referring to is a prehensile tail. Fully prehensile means you can carry your weight on the tail.
Mm-hmm.
You can hold your entire weight up with your tail like it is a true arm. Semi-prehensile cannot support your weight.
Right. Which is true of most animals, by the way. Don't go around picking up animals by their tails.
No, that will hurt the spine of the tail.
Yes.
That can dislocate joints. Even if they have a grabby tail, like mice have a semi-prehensile tail where they can wrap it around things, but they're not hanging from it. Mm-hmm. We see this feature in tons of groups, separately evolved many, many times. We talked about this feature in seahorses and their cousins back in that episode.
Episode 136.
Also, which seems to have evolved multiple times in seahorses and pipe horses there. We see it in many salamanders will have long semi-prehensile tails. Often when they describe groups that just have one version of the tail, they'll just call it prehensile. Also, it doesn't apply to seahorses who are never holding their weight.
Right, you're not supporting your weight because you're in the water.
Like, I'm sure you probably could, but we can never test that without hurting you. So the terms are often used interchangeably. That prehensile is just used generally for a flexible, grasping tail. There was one salamander I found note of, a very tiny one, just like a few centimeters long, that will use their tails when they're falling as a hook.
So, like, catch onto a branch?
Yes.
Oh, cool.
To catch themselves before they hit the ground. In mammals, it has happened tons of times. There are at least 14 different individual evolutionary origins of prehensile tails in mammals across 14 families.
Wow.
Primates are probably the most famous that you'll think of.
Yeah, tons of monkeys with prehensile tails.
The most noteworthy are the New World monkeys, your South American monkeys, which include spider monkeys, howler monkeys, and the like. Many of these have the ultimate prehensile tail. Truly prehensile, they can carry their whole weight on the tail, often with having a special grasping pad at the end for holding onto the branch, like the palm of a hand.
Yeah.
Like, this is as close as we've really seen to having a fifth limb, a fifth arm, and they are really good at them. Now, we do see that it also has evolved multiple times within this group, with some having semi-prehensile tails and fully furred tails. These are going to be your Cibidae, which are things like squirrel monkeys and capuchins. And then your spider monkeys, your howlers, have fully prehensile tails, the Attilidae. Now, here's one of my favorite things that I found while looking at all this. The structure of a prehensile tail is different from other tails, which is not surprising. Mm-hmm. But specifically, there are two sections to it. The proximal section, that is closest to the body, which is most of the length, and the distal section, which is the rest of the tail, the tip of the tail. We see a number of structural things that strengthen the tail, give it more mobility, give it more muscular control, and make it able to carry more weight and do more. But the distal portion has notably shorter and more flexible joints, more flexible vertebrae, so that it can curl more effectively than the rest of the prehensile tail. So just like our hand is better at grasping than my elbow is, mm-hmm. The rest of the main portion of the prehensile tail is great at holding itself and holding up weight, but the tip is really where most of the grasping specialization is.
Wow, that is a lot like an arm with a hand at the end of it.
Yes, it is.
Where it's the longer bones and fewer joints along most of the length, and then at the end you have shorter bones with more joints. That's, wow, you weren't kidding.
Yep. And my favorite thing is we see the exact same pattern in chameleons.
Oh, cool.
Chameleons, those alternating eyes, their separate eyes and long shooting tongue, they often have a prehensile curled tail, And once again, the tip has a specialized section of shorter vertebrae, better at grasping.
Wow, that's some cool convergent evolution.
Yeah!
The other thing that's cool about that is that is a distinct anatomical feature in the bones of the tail, which means that we could potentially identify that in fossil remains.
Absolutely. And it's very likely from an evolutionary standpoint, and we could look for this in the fossil, is that from what we can tell looking at the monkeys that have our two groups of semi-prehensile and prehensile, it's likely that the semi-prehensile was transition to fully prehensile, that you got a slightly more maneuverable tail, and the ancestors of our fully prehensile probably had capuchin-like tails that were furred and not as grasping and not able to hold their weight. And even before that, as we mentioned with the marsupials using their tail as support, we see many tree-dwelling animals use their tail as kind of a kickstand.
Mm-hmm.
Basically, picture a position where they're holding on with their back feet and then using the tail to hold or support so they can either raise up like a tripod or to hold onto the branch with the tail and the back feet and lean down off the branch. That's how we see many of the semi-prehensile monkeys use it. And a step up from that is just holding on with the tail alone.
Yeah, that makes sense.
But tails are also specialized for many other forms of interaction and behavior. We see tail displays. We see tails used for fat storage and stuff like that.
Sure.
So there's lots of other features. One that I wanted to zoom in on a little bit just because it gets super weird is defense.
Yeah.
Tails are very often used as a defensive tool, weapon. You see lots of whipping of tails. Skunks use their tail as a display to ward you off before they spray you and stuff.
As a threat.
Yep. You see lots of tails used to ward off enemies or predators very, very often.
Yeah, either as a physical strike or like a rattlesnake to do something to scare you away.
Rattlesnakes are probably one of the most famous for tail defense, where they use that rattle, the specialized loose scales at the tip of the tail, which has even specialized rattle muscles at the end of the tail.
Yep, with specialized features on the tail bones to support those muscles.
So you have a very, very specialized tip of the tail that they can then rattle, making a very loud warning of, don't step on me, don't come near me, I am venomous.
I am a rattlesnake, you stay over there.
Don't mess with me. Which very often gets portrayed as this threatening thing. But the point is, I am a small snake, and you have big heavy hooves, you bison, you.
Yes, please don't come over here.
Please stay away from me. I don't want to get trampled upon.
Yes, being scary is my defense.
Yes, I'm warning you off. I don't want to bite you. I'd prefer we just don't interact. So stay away. Now, this is a extremely unique feature. It is only found in rattlesnakes. No other group of snakes, as far as we've ever found, has ever evolved a rattle.
No, lots of snakes will shake their tail.
Absolutely.
In the leaves, in the leaf litter. My pet snake does it against the glass of the terrarium.
Yeah, that is an extremely common behavior. It's found in most vipers and across the colubrids, which are your other very large group of snakes.
Yeah, very common behavior.
And one research took a look at to see, is this likely where the rattlesnake tail came from, the behavior originated from, and they measured the tail vibrations of 56 different species of snake and compared the duration, how long they did it, and the rate, the speed.
How quickly they're shaking.
Exactly, and they found that closer relatives of rattlesnakes had more similar rates and durations.
Yeah, that makes sense.
So
it just got better and better and better until you had a proper rattle.
Yeah, until you started evolving a specialized structure.
And rattlesnakes shake their tails at a much faster and more efficient rate than most snakes that are doing little tail rattles.
Absolutely. And the other rattles would be like shaking leaves and rubbing up, knocking up against something to make the noise.
Yeah.
But this is not the only form of tail defense we see in snakes. One other very common form of tail defense is head mimicry. We see this in lots of lizards where they'll have tails similarly shaped to their heads.
Yeah, it makes it hard to tell which end is which.
Exactly, that it is just a potential distraction that maybe you'll aim for the part that doesn't have my brain in it. Snakes will often do this. There will be snakes with blunted ends of their tails. One really interesting example is coral snakes, specifically the variable coral snake. Coral snakes, a famous group of venomous snakes that often have banding patterns on their body to signify that they are venomous. They're also famous for being mimicked by other snakes. This species of coral snake, at least, and many of their mimics, will often have tail displays to mimic their head as well. In many of them, the tail has a similar banding pattern that the head has, and they will put on a display. When attacked, it's been noted that they will place their head under their coils or just keep the head still in a striking pose, and then they will either flatten or curl the end of the tail to make it a more bulbed head shape. They'll sometimes also flatten out their body in like a hooding, kind of like a hooded cobra, and then they will move the tail tip similar to the head, even false striking with it.
Very cool.
To give the indication that the head is in this end and maybe even dangerous.
Yeah, a very elaborate mimicry of the other side of the body.
Absolutely. But probably one of the most famous tail defense strategies that you'll find is losing your tail. This is found in lots of different groups where they will shed their tail when attacked.
This isn't evolutionarily losing it like in apes have done that, but having a tail and the ability to just pop it off and run away.
Yes, shedding your tail.
Yes, lots of lizards do this.
Lots of lizards do this. Lots of salamanders do this. The shedding of a body part is known as autotomy.
Or autotomy.
Autotomy. And we see it in tons of groups. Arthropods very often do this with their limbs, and many animals have evolved to do it with their tails. This is often in response to a predator action, that they are attacked or the tail is grabbed, and then they will disconnect the tail, leave it behind while they make a getaway.
Yeah, and this isn't just that the tail gets ripped off. There is a special mechanism built into the tail to let it do this.
Yes. True autonomy is self-induced, that the animal triggers it itself, and it is along a plane, a breakage point. This will either be between the backbones.
Yeah, between two vertebrae.
Yep, we'll call this intervertebral autonomy. Or there will be breakage points among typically a series of vertebrae that break there at that vertebrae. And this is intravertebral autonomy.
Yeah, where the bone itself actually splits to allow this to happen.
This is the more common and typically sees the more complex neurological control. Some animals can detach their tail without any outside stimulus.
Yeah, they can just decide to do it.
I watched a salamander do this as a kid one time, where I was trying to get it out of our house. It was getting covered in dust because it was walking around our floor. And I tried to pick it up, and I didn't even touch its tail, and it just wiggled its butt, and the tail popped off. It just disconnected the tail. That breakage plane will then seal very quickly to keep them from bleeding, so it heals up or closes up extremely fast so that they can now move around and survive without that tail. Many will have a secondary feature where the tail is either brightly colored to distract and hopefully direct attacks to it, but super commonly, the tail will twitch.
Yeah, it'll wiggle around.
It'll wiggle around, continue to move, and draw attention to itself.
Yeah, so the predator hopefully goes for the tail.
This is very common among many of your break the tail off before I'm actually attacked.
Yes.
I will break it and leave it as I'm already running. While others, the tail is grabbed, and that is the physical trigger. That then I cut loose and like throwing my jacket off as I'm running away from you. I keep running. Now, this feature has evolved in different groups, separately it seems, and the question comes in, how do you evolve cutting a limb off? Like, that's a very unusual physical characteristic, and there are two main hypotheses. One, called the intermediate step hypothesis, suggests that autonomy arose for a different reason. That they evolved to lose a limb, and this goes for tails, but as well as legs and arms and crabs and spiders and so forth, that you evolved to lose that limb for some other reason, and it was secondarily used to avoid predators. One of the most common suggestions is to cut down on the cost of an injury.
Oh, okay.
If you're a spider that breaks a leg...
Self-amputation.
Exactly. Self-amputation. This could also happen if there was an infection, or if there was, I saw one even note, buildup of toxins or something.
Yeah, well, and that makes a lot of sense if you think about something like a spider who has plenty of legs.
Yes.
Or a vertebrate, you have a tail, and the tail is often very important, But you can afford to lose a tail more, for example, than you might be able to afford to lose an arm.
Exactly.
Or a head.
Yes. And that's one of the key features of autonomy, is that it is typically in a not necessarily non-crucial, but non-essential body part.
You will survive without that end of the tail.
Exactly. The other hypothesis, called the false latency hypothesis, suggests that it was first for anti-predation, but it wasn't to break the body part off. First, it was just to direct attacks that way. Having a pattern that directs attacks toward the tail, like the head-shaped tails. Or potentially just a part of the body that tended to get attacked more.
Right. It wiggles around more, it's more brightly colored,
or
it
just is more accessible, like the long tail. If you have a long tail, that just might be easier for me to bite when you run away from me and point your butt at me. Like, it just might be a part that statistically is getting more attacked more often.
Right.
Then the next step in this hypothesis is that appendage would become easy to remove. Either it breaks easily, it fractures, or it is just easier to come off when it is damaged.
Right.
It is not triggered to come off by the animal, but it is just more easy to be removed when it's attacked. And then eventually the self-control of shedding that limb and quickly shedding it comes into play.
Yeah, that makes sense. It also makes sense to imagine the tail becoming less dire to lose.
Yes.
That if you can evolve a pattern of nerves or blood vessels so that if the tail does get taken off, you don't bleed out, or it's not quite as crucial an injury as it otherwise could be.
Exactly. But, and that brings us nicely to the next section, losing a tail is costly. Even if it helped you survive that predator attack, you're still down a limb now. You're down an appendage, so to speak. This is going to affect mobility for animals that are using it to balance, lizards that are using it for balance. There are many lizards that use it as a support while jumping to lean back and leap, and losing a tail is going to reduce that capability. If you were using it as fat storage, you now lost that fat stored and the ability to store fat there.
Yeah. You've also lost the ability to ward off a predator.
Yep. You don't have that get out of jail free card anymore. If you use your tail for displays, you now might not be able to mate effectively. Like, it is very costly. Probably the most costly of these that I found was that scorpions have been known to shed their tails.
Huh.
Yeah. And they also twitch around. They have true autonomy, but they suffer from the fact that their tail includes part of their digestive tract.
Oh, yeah, it sure does.
And their stinger.
Yeah, which they use for hunting.
Yes. And so therefore, when a scorpion sheds its tail, it loses the ability to sting anything, and it's not going to get that back. It's not going to grow its tail back, which we see in many other groups, and it loses the ability to poop.
Right.
So scorpions that have lost their tail stop going to the bathroom and stop being able to sting, which means that they can still feed, but they can only catch small prey that they can kill with their claws alone. And it's been noted in a laboratory that they basically have a time limit of about 8 months. Once they've lost their tail, they're on borrowed time.
Yeah.
But they can still feed themselves, and they can still mate.
Yeah, and I was going to say, at least 8 months is quite a good chunk of a scorpion's life to still get some stuff done.
Precisely. So it is still an effective defense, because I can still eat, and I can still pass on my genes.
Yeah.
But because it is so costly, regeneration has evolved in many groups that lose limbs, that lose body parts, and in tails that is no different. We see regrowth of the tail quite often. Lizards, once again, are the famous one that this is pointed out. That's why the lizard is the bad guy of Spider-Man, is the regrowing a body part.
Yes, even though the lizard does it way more effectively and efficiently than a real lizard would do.
Yes. It's also regrowing their arm, which is not what lizards do.
No.
But they can regrow lost tails. Typically, though, these tails are not the same as the original tail.
Yeah. Oftentimes you can see the difference. It's very obvious that this is a second tail.
Yeah, there's discoloration. The patterning, if there was patterning, is different. The scales sometimes will be different. There will often be a notable pinch at the site of regrowth. Mm-hmm. And internally, it does not regrow the same structures. They cannot regrow the muscle, nerves, and bone. So a regrown lizard tail is just a rod of cartilage with some tissue and skin around it.
Mm-hmm.
But typically this does regain all of the main needs of that tail, like mobility, like display. It does mean, though, that they cannot shed that cartilage. But they can do two interesting things. Most lizards have multiple vertebrae that they can break to shed the tail. If they shed the last of those breakable vertebrae and then regrow a cartilage tail, they can then shed the next breaking point.
And break it again.
And then again, slowly moving up toward the body, which means they have like, you know, shots in a pistol. They have a certain number of times they can do this throughout their life, but they could reshed it as long as they have a further up breaking point. And they can regrow the cartilage. If it's like chopped off or bitten off, they can regrow the tip that was removed. They can't shed it. They can't lose it on purpose. But if it is removed forcibly, they can regrow it again. That regrowing of the cartilage has also been called regeneration, and I think is mostly anecdotal, but it's been noted in king skinks. So
interesting.
That's one where maybe we'll find out that not actually as much as it's been claimed, or maybe not as common. The group that is by far noted for being best at this, though, is salamanders.
Yeah.
Who can regrow a true tail. Bones, nerves, muscle, blood vessels, identical to the original. They're also able to do this with limbs.
Yeah.
Like, they're really good at
arms and legs.
They can regenerate like crazy. And many of the genetic signatures between salamanders and lizards are very similar in their tail regrowth, which suggests this might be ancestral to tetrapods, to legged vertebrates.
Yeah, that this is something that we mammals can't do because we lost that ability at some point.
And when we look at other groups, it seems to support this. There is fossil evidence of early tetrapods regrowing their tails.
Yeah, because we've been talking about the way the bones are structured and the way that the bones regrow or don't regrow. That's skeletal anatomy that we can find preserved in the fossil record, and we can find evidence of autotomy in fossil animals.
There's one genus called Microbranchus that there are at least 2 specimens that show different phases, different points in the regrowth process, showing them regrowing what seems to have been a purposely shed tail based on the features, and shows that they regrow it more similarly, like the development of the new tail, to salamanders, but the breaking seems to be more similar to lizards.
Oh, interesting.
Yeah, where most squamates have intravertebral, breaking on a vertebrae. Salamanders tend to break between intervertebral.
Okay.
So it broke its tail, it seems, like a lizard, but is regrowing it like a salamander.
Cool. So this is something that has developed in different directions over time.
Absolutely. So it seems like, yes, early tetrapods, early land vertebrates were able to lose and regrow their tails, and even more so, lungfish can regrow their tail.
Oh, interesting.
The West African lungfish have been noted to be able to fully regrow their tail, perfectly a new tail, which seems to suggest that this may be ancestral to Sarcopterygians, the lobe-finned fish that early tetrapods evolved from.
Yes, our nearest fish cousins also have this ability.
So it seems like this is a feature that the lineage that led to land vertebrates had.
Yeah, and we mentioned that salamanders and lizards are very famous at this, but we did a news not too long ago that showed some degree of this ability potentially in alligators.
Absolutely. And there's like the tips of some mammal tails. Like not the tail, but like if you chop just the tip off, which I'm not saying to do that.
Right, don't do that.
But it's the same way we can regrow our fingertips.
Yeah.
Like there is a little bit of regeneration even in us for those extremities.
Yeah, so getting the tail back might be something vertebrates have been doing for a long, long time.
Yeah, basically since we started coming to land. Now at this point, we're going to take a brief break, but come back and talk even more about the fossil record. So since we've looked a little bit about the ancestry of tail regrowth in us vertebrates, there's a bunch of other things we can look at in the ancestry of tails, and also just tails from the past, both to look at more variety and also what we can tell about those fossil animals based on their tails.
And also we can talk about dinosaurs.
Woo! Before the break, we talked about the origins of tail regeneration in vertebrates. Now let's talk a little bit about the origin of tails in vertebrates. So vertebrates, your backboned animals, which include fish and all of your land animals with 4 arms and legs, and then those who have lost them and stuff like that, ancestrally had tails. This group, our lineage, started with tails.
Yeah. Started as fish. Fish have tails.
Precisely. And the ancestors to fish, which are likely something similar to lancelets or amphioxy today, which closely resemble the pikaia, which was swimming around 530 million years ago and is likely either an ancestor to vertebrates or very similar, very close to, are these just kind of feather-shaped organisms that swim like a fish, not as effectively as fish, but they swim like a fish, and they do have a little tail fin at the end. Mm-hmm. Very simple tail. It's not as differentiated as it is in later groups, but it is there.
Right. It's mostly a long body. It actually kind of reminds me of when you were talking about lobsters.
Yes.
How it's a long body and then there is a fin at the end that is helpful for swimming.
Precisely. So it's likely that the ancestor to all vertebrates had a body shape similar to this. So we already were using a tail-like structure to swim from the beginning. But there has been research into what the ancestor tail would have looked like. Today, when you think of a fish tail, you've got the tail and then the caudal fin at the end, the tail fin, which acts as the paddle and the propeller, basically, the propulsion.
The actual tail, the long extension of the spine, extends to the very end of the fish, and then there is fin coming off that body that's just soft tissue. Similar to if you think of a dolphin.
Yes.
The bony tail is in there, but then it has the flukes that go off to the side to act as the paddle.
Yeah, which are kind of add-ons to the end of the tail. But when you look at early fish, you see a very different shape of tail, where they have what looks like, if you think of a lizard tail sticking off the body, and then the fin running underneath that. Much more like knife fish today, or many of your eels, which will have fins along the body.
Right, kind of hanging down from the tail.
Precisely. This is extremely common with your early Paleozoic fish. One genus, which is Ethritmon,
which I'm sure digivolves into something.
Oh yeah, no, something completely random with belts and guns and randomness. This is a group of fish from almost 350 million years ago that is a cousin to early ray-finned fish. Ray-finned fish are most fish you think of with those see-through fins and the long rods that support them. This group, though, bears one of the oldest ontogenetic growth series records for this group.
So we can see, we have examples of young all the way up to adults. We can see how they grew.
Absolutely. And like we will often see when we look at the embryos and early development of animals today, it is very common to note ancestral features in the early development, that we have a more notable tail as an embryo human that gets absorbed during our development, but it is there because ancestrally we had a tail. So they looked at the early phases, the early forms of these fish to get an idea for what was the ancestral form of these ancestors, very much like. And what they found was a 2-part tail.
Huh.
That when you think of that early tail with the long tail up top and the fin on the bottom, those were separate structures in the early phases. With a top lobe that was tail-ish but had a little fin at the end, and then a bottom rounded lobe that would become the bottom fin.
Huh, so I'm kind of thinking like a butterfly wing.
Yeah.
That gradually merged into just one big wing.
Yes, exactly. This matches some early stages in today's fish, the teleosts, which are your ray-finned fish, and seems to represent that this is likely what the ancestral tail form is, some form of 2-tailed fish setup.
Interesting.
The cool thing is that the tails we think of today with the fin at the end and those old tails with the fin along the bottom are just the same parts, but positioned differently. The old tail is a long upper section with a shorter bottom section along the bottom that have fused. Today's fish have a short top section. The bottom section has wrapped around it to form the caudal fin.
Oh, okay.
The tail fin of a fish is the bottom tail from that ancestor.
That has extended upward to create a fin that extends both up and down.
Yes. And the top tail is short in today's fish. It is much reduced compared to the old fish where it would actually go past that bottom fin.
Yeah. So the tail has shortened so the fin can wrap around and extend upwards. So even fish tails, which seem like the tail, the original tail, have changed quite a bit over time.
Oh, yeah. Like, I don't even fully know how to picture that ancestral tail. Like, I don't have an image in my head for what it would have looked, because that sounds super weird.
Yeah, it sounds like just a tail that went out straight, and then there was like, I'm picturing like the dewlap on a lizard's neck that just kind of hangs down, like a fin that just hangs down like that.
Yeah, except with the young, it sounds like they were notably separate.
So maybe my butterfly.
Yeah, something.
That's a strange.
It's weird. It's very weird. But that means that vertebrates ancestrally have tails. We all come from the fish tail.
Yes.
And throughout history have done weird things with it. Now, one section we did not touch on in our first part that is very fun to talk about in the fossil record is tail weaponry.
Yeah, we talked about tail defense,
Yes.
which butts right up against this, so to speak. And today we have animals. Scorpions use their tails as weapons.
Absolutely.
There are lizards that will lash with their tails as just swinging around and hit something.
Yeah, and sometimes to fight rivals, so it's not just defensive, but it is aggressive.
Yep. But, yeah, in the fossil record, there are a bunch of really cool examples of this.
And we talked about one just last episode.
Episode 150, we talked about stegosaurs.
With their thagomizer tails.
Thagomizers. And we talked in episode 69 about their cousins, ankylosaurs, which often have clubs on their tails.
Precisely. Now, we find some interesting trends when it comes to tail weaponry. One, it is rare.
Yeah.
There is a diversity of it. Many groups have come to it, but generally, it is not the common tail adaptation.
Surprisingly, considering how many animals have tails.
Yes. And it has been noted, research has found a trend between the evolution of tail weaponry and the presence of large body size, body armor, and herbivory.
Oh, yeah. I think we may have talked about this study in the news at some point.
Yes, I think so. That typically we see tail weapons evolve in groups that are big, eat plants, and have armor.
That it does make sense. We've talked in both ankylosaur and stegosaur discussions that the clubs or spikes on the tail are modified osteoderms, which is the bony armor that they already have across the other parts of their body.
This may also explain why tail weapons are as rare as they are, because big armored herbivores are also not super common.
Yeah, that just doesn't happen very often.
But when we do, sometimes it can get really similar. Now, we may have mentioned glyptodons in the ankylosaur episode.
We might have mentioned them as a comparison.
Yep.
Glyptodonts are cousins of armadillos, and they look like, going back to my Digimon reference, it looks like if someone took an armadillo and asked a cartoon or sci-fi creator to say, what if this turned into the monstrous, super extra version of itself?
Yeah. If armadillo's the rookie form, what's the champion form?
Yes, and it's just, glyptodonts are these often Volkswagen-shaped and sized animals with just a big dome of armor, and often with a tail that sticks out the end. That is weapons.
Yes.
Weaponized.
And, continuing that Digimon reference, ankylosaurs would be the ultimate level next up, because the tail weaponry on glyptodons and ankylosaurs are super similar.
Yeah. Glyptodonts lived very recently at the tail end, I guess, of the Cenozoic, the last several million years. They're very famous from the Ice Age, which is very recent.
Yep.
Whereas ankylosaurs are most prominent from the late Cretaceous.
Yes.
So they're separated by a good 60, 70 million years.
Yeah, the very oldest glyptodon fossils go back not quite 40 million years ago.
Okay, that is older than I thought, actually.
But they did not yet have tail clubs.
Okay.
They had armored tails with rings of osteoderms that were flexible still. So just an armored tail, but not something quite weaponized.
Right, so like the bands of an armadillo's armor, but just continuing down the tail.
Yes, sometimes they'd be spiky, but not specialized for doing damage, just not friendly to bites. More derived and later groups of glyptodons often had tail clubs, which were typically formed where the distal end, toward the tip of the tail, would have what's called a caudal tube, a rod of fused bone that would act like a baseball bat, a club. And then a couple of groups expanded the end of that club into balls or spiked maces.
Yeah.
Just like we see in ankylosaurs.
Medieval weaponry.
Yes, and when studies looked at the tails of these two, because it's been suggested that these were convergent, just at a glance.
Sure.
But one study looked in to see how similar are they actually, and found that 80% of the morphological features can be explained by convergence.
Wow.
They are effectively 80% similar in how they've evolved.
Which makes a ton of sense given how rare this is, that there is perhaps one way to do it really well.
Yes, and once again, both very large, both herbivorous, both highly armored.
Yes, and both lived in ecosystems with large predators, not to mention other members of their own species.
Yep. Now, we do see tail clubs in other groups. There are some sauropods that have little clubs at the end of their tail.
Oh, yeah, so the long neck, long tailed dinosaurs. Omesaurus is one of those, I think, with a little club at the end.
But it's often been suggested that maybe they used their tails as weapons even when they didn't have specialized features.
Yes, that sort of whip-like tail. And you'll see this in documentaries and movies and stuff. The sauropods will whip their tails at a carnivore or something.
I found one study that described their tails as hyper-elongate, that they have extremely long tails. Some groups are especially well known for this. The diplodocids and the apatosaurines have very long, very thin, super whip-like tails.
Yeah, this includes Diplodocus, Apatosaurus, Brontosaurus, those kinds of dinosaurs.
These can have up to 70 to 80 vertebrae in them and be up to 10 meters long.
Yep, just keep adding vertebrae and they're big.
Yes. Which fits our big herbivorous.
Sure.
Sauropods are large animals. They are plant eaters, and many of them were somewhat armored.
Yeah, a lot of them had osteoderms.
Yeah. And there have been studies to look into, would these tails have worked as a whip-like structure? And a couple were done in the 90s. One more recent study made simulated tails of one based off of apatosaurine, one based off of diplodocine tails, each which were about 12 meters long and included 82 segments that were representing the vertebrae. And both models showed that they were able to surpass the speed of sound, meaning they hypothetically could create the crack of a whip.
Yeah, just with the ability to move the base of the tail with their normal musculature would ripple down the length of the tail, and by the time it gets to the end, that is a very fast crack of the tip of the tail.
So you'd get that pow that whips are able to create, which could have been used either as a direct hit, like that's the point of the whip that you aim when you want to really hit with a whip. That burst of breaking the sound barrier is extremely strong and impactful, or it could have just been a noisemaker.
Right.
They did note like diplodocines were able to achieve 4 times the speed of the apatosaurian tail. So some of these get quite fast. Like both were able to do it. One was 4 times faster than the other.
Right. Now, this is one of those cases where it's important to note the distinction, as we've talked about before, between what animals could theoretically do and what they actually did.
Yes.
So these are models that show that this was theoretically possible. This has been questioned on the grounds that A, that even if they could, maybe they didn't.
Yep.
But also the suggestion that even if they could do this, could their tails survive that? Would that just damage the tail a whole bunch to try to use it that way?
It's sort of like you may be able to throw as fast as a baseball pitcher, but if you don't know how to do it, you're going to throw your arm out.
Right.
Like that is an action that is very likely to damage you, even if you can do it.
Oh yeah, I have the strength to punch through a window, but I don't want to, I will hurt myself immensely if I do that.
Yep, you'll be able to explain it at the hospital.
Yes.
And very obviously, many other purposes for this tail have been suggested. Counterbalancing, display.
Oh yeah.
One that I found in a recent study is herd coordination. It is very well known that sauropods moved in groups. We have many footprint trackways and burial sites showing that they were herding and group living animals. And it is thought that maybe with these long tails, it would kind of act like the lateral lines on a school of fish, able to help them keep track of the movements of the herd and move as a unit more effectively by just keeping slight touch with the other sauropods around them.
Oh yeah.
Instead of stopping and pausing every time they needed to change direction.
Looking over your shoulder.
Yep, and waiting for each other to catch. You would just kind of be in light contact with each other based on these long tails.
Interesting.
So there's many other potential answers for what this tail was used for other than an Indiana Jones whip.
Right. And we did talk about these concepts and more in episode 101 about sauropods.
Absolutely. Now, all of these tail weapons have been defensive. As you mentioned, scorpions also have tail weapons which can be used defensively, but are primarily hunting weapons.
Yeah, we've talked in the ankylosaur and stegosaur discussions, and you mentioned it just a little earlier, that some of these could be for competition, that they are a bit offensive, they're aggressive, you're using them to ward off rivals and stuff, in addition to possibly using them against predators. But scorpions are an example of very much, this is meant to take things down, because I need to do that to eat.
Yep. And they are not alone. There are other predatory tail weapons. My favorite, just because it's so weird, is the thresher shark.
That is a good one.
Thresher sharks are a group of lamniform sharks that have a very long tail fin. Specifically, the top part of the tail fin just goes out into this ribbon, and they can use these tail fins to whip at schools of fish and stun them, stunning individual or small groups of fish. Some have even been noted to slice the fish with the edge of the tail.
Ooh.
I don't know how for sure that is, but I've seen that noted before, that they can actually injure the fish, not just stun them, but they will use this tail as a way to not just corral prey, which we see in other groups, like gharials, the long-snouted crocs, will use their tail to trap a group of fish so they can eat at them.
Right, and that's really using your long body to help keep your prey in the position you want them to be.
This is a predator actively catching its prey with its tail.
Yeah, whipping at them with that long tail.
This has also been suggested for fossil groups. The most famous, unsurprisingly by their common name, are sea scorpions.
That's true, the Eurypterids.
The Eurypterids. This was an early group of mostly aquatic arthropods.
Not true scorpions.
No. These are known from the Middle Ordovician to into the Permian, which is about 460 to 250 million years ago. These were cousins of chelicerates, so cousins of the group that includes scorpions and spiders and mites and stuff. They have typically long bodies, flattened bodies with paddle-like back limbs. Their back of the body is often elongated into a tail-like structure. This would be similar to the metasoma of the scorpion, with the tip, the telson, being a typically leaf-shaped spear tip, often spiky structure. This is the group that our Displacer Beast was based off of.
Yes, in Spooky
this
year.
Yep. So if you haven't listened to that, go back and listen to it because it's awesome. This group was very diverse, some of them getting very large, and based on the fact that they had claws up front and that spiky tail, they got the name sea scorpions. But it has often been questioned how they actually used that tail, because it doesn't seem like it could flex up like a scorpion's tail over the body. It doesn't bend that way. So they definitely weren't bending like a scorpion. So it was often thought that it was probably just more for swimming, using it as a rudder, not swinging it back and forth like a crocodile or a shark because it was flat, so it wouldn't have made much of a thrust. It would have been good for steering them as they paddled along. But one specimen that was described in a study in 2017 showed a fully articulated Eurypterid fossil with the tail curled around to the side of the body, one side, with the tip coming much farther up than we had thought it could. Which the authors suggested indicated that it could have been used as an effective weapon either for defense or predation with a sideways strike.
Yeah.
Whipping the tail to the left or the right of the body up toward the prey or its potential predator. This, though, has been brought into question the very next year, where another paper went through and said, we disagree.
Mm-hmm.
We think that's actually a molt, a shed skin, not the animal. We think that bending is due to after-death events, not life events.
Right, which I was going to bring that up, that, again, the thing an animal can do versus the thing that it would do.
Yes.
Sometimes a fossil is bent into a shape that isn't actually feasible in a living animal.
They did note some separation of the segments and overlapping of the segments that suggests that this was overextending.
Yeah, it would have broken the body to do this.
And they did a hydrodynamic study that did not seem to support that the tail would have been a efficient weapon moving through the water.
Gotcha. Just to get it moving that way when you're underwater.
Yeah, that it would not actually have been an effective strike.
Okay.
So you'll see many arts nowadays depicting them striking with a tail because of that first study, but there was a study that followed up directly after and countered basically every point.
Okay. So
maybe
ambiguous at best.
Yes. Now, one of the other things we use tails for in the fossil record is to interpret the lifestyle of the animal.
Oh yeah, we mentioned earlier that the length of the tail can correlate to habitat, things like that.
Yes, so there's lots of things where we can look at the features of the tail and get inklings about what the lifestyle, what the habitat, what the behaviors of that organism might have been like.
Just like we can do with limb bones and the shape of the hands and the feet and the arms and the legs.
So let's talk a little bit about some of the ways and some of the times we've been able to do that in the fossil record. And I thought it would be fun, since we've already mentioned the other groups of dinosaurs that we've done episodes on, to do this one on theropods.
Oh.
The two-legged, mostly predatory group of dinosaurs, which had long tails very often that stuck off the back of the body.
And there has been so much research done on the tails of theropod dinosaurs, your T-Rexes and your Allosaurs and your Velociraptors and such, because they are such prominent structures.
Absolutely. And very often it was thought that they just acted as a counterbalance to the front of the body on the pivot of the two legs.
Yeah, they're like a seesaw.
Yes. But one study that looked at Coelophysis, which was a small theropod, simulations of the tail and its movements and flexibility when walking would have occurred seemed to indicate that it was not just acting as a static counterbalance rod, but would actually flex side to side with the motion of the body, acting more similar to when we swing our arms while we walk to counter the movement of the body and act as a dynamic weight balance.
Yeah, it's a stabilizer.
Yeah, like a metronome again, swinging the weight of the tail in opposition to the stepping of the body to keep things balanced and stable. So it's likely that it would have been a fairly dynamic physics structure that aided the physics of motion while they were walking around on two legs. There's also famously been study into Spinosaurus's tail, speaking of motion.
Sure.
And its features that seem to indicate quite strongly that it might have been used for propulsion while swimming in water.
Yeah, there has been some recent research, recent enough that I don't think it got mentioned in episode 42 when we did a whole episode about Spinosaurus.
Yeah, precisely.
That showed that the tail might have been tall and flat.
Yes.
Which we see in crocodilians, and we see it in fish, and we see it in sea snakes and animals that are using their tail to move in the water.
Yeah, the way I see it drawn makes me think very heavily of salamander tails.
Yeah.
Just this long, almost continuously tall and flattened tail. Robotic simulations of this tail have seemed to support that it would have been decent at propulsion.
Mm-hmm.
So that's another sense of movement that we're getting from the tail. Surprisingly enough, there's even been evidence of senses from tail fossils. One late Jurassic theropod, Juravinator starki, which is small, like 75 centimeters.
A little tiny theropod.
Just a couple feet long, is known from only a single specimen, but a very well-preserved specimen that has skin impressions. And the scales on the tail preserve what seem to be sensory scales, sensory organs similar to the pressure sensors on crocs. When you look at a croc's jaw, you will see little black dots, little black pits all along its teeth and around its mouth. These are temperature and pressure sensors that allow them to sense water movement and environment temperature. This seems to be similar scales for those kinds of sensory organs on the tail.
Oh, fascinating.
So evidence from this tail seems to give an indication for some of the sensory ability of this animal, likely suggesting it had it elsewhere, which then suggests that it might have been using this somehow in its life, which, based off the sclerotic ring, which is the ring of bones around the eye, it's likely this was a nocturnal animal, a nocturnal predator, which means that any extra sensory info you could get would be helpful in a low light environment.
Yeah.
While crocs seem to only use theirs in the water, for pressure, temperature could still be helpful, but it may have suggested that Juravinator was sitting in the water, maybe aiding itself in capturing aquatic prey by submerging these scales. Maybe it wasn't living in the water, but this was an additional way to hunt. So we have info into a unique physical adaptation of this animal because of the tail fossil.
Very cool.
Right? We've also found cases of potential sexual dimorphism, where the male and female of the species are physically distinct from one another in tail fossils. Oviraptors, which is a whole group of theropod dinosaurs that are famous for their flattened beak-like faces and crest on the head and often very ornate feathers. It's been suggested in the past that they likely use their feathers for courtship.
Mm-hmm.
And in those suggestions, it was hypothesized that we will likely find evidence, or would find if we were able to, of sexual dimorphism if they're using it for courtship, since we see that in feathered dinosaurs today. And in fact, two specimens of the Oviraptor Con McKinney, who are both very similar in their size and all other anatomical features except their tailbones are different. One has anterior hemal spines, which are spines coming off the bottom of the tail, that exceed the length notably of the other specimen, and had a unique spear tip end, like a spiky end to those spines. They also offered greater surface area for tail muscle attachment on those longer spines, which seems to indicate a sexual dimorphism between these two specimens, likely a male tail with the longer spines and a female tail with the less notable spines.
Yeah. Now, it's always important whenever we bring up the subject of sexual dimorphism in dinosaurs that basically every case of that has been suggested has been challenged.
Yes.
Because that can be very difficult to know. But we do know that lots of dinosaurs had extensive feathering on their tails.
Yes.
There have even been some that have been shown to have feathers that don't seem to serve any purpose beyond display. So it would not be surprising to find differences between males and females in the tail feathers.
And this is one of the reasons they emphasize that these are the same species, same size, and seem to have the same features everywhere else.
Mm-hmm.
But here, and they noted that these differences are too extreme for individual variation, which is why they lean towards sexual dimorphism. But yes, it is very difficult since we can't actually determine the sex of each animal. But they have been nicknamed Romeo and Juliet or Sid and Nancy.
Sure.
So that's their names now. We'll also find evidence of truly unique lifestyles based off of tail and other features. One group that's famous for this, which I didn't know they were notable for their tails, are the Alvarez-saurs. This is a group of maniraptoran theropods, which includes birds. These are closer to there. They are notable for having long back limbs, likely for a running lifestyle. And their weird features come in that they have reduced jaws and teeth and special forelimbs that typically have large second digit claws and reduced claws elsewhere, many of the group having only one claw on the arm. Mononychus is a famous one of this. Its name coming from the fact that it just has one claw on each hand on those front limbs. The reduction in teeth and the clawed arms has often led them to be speculated to eat colonial insects like termites and ants.
Mm-hmm. Like an anteater.
Like an anteater, which has claws and reduced teeth. But their tail is also notable. One, it is the longest proportionally of this whole group of theropods. Very long tails, both in the number of vertebrae and the proportional length. So they have very long tails, some of them having 35 vertebrae in the tail.
Wow.
So long tails compared to their body, with features that suggest both more mobility to the tail and more musculature to the tail. This has been interpreted to potentially have a couple uses. One, simulations have suggested it would make them very good at turning while running, using the tail as a counterbalance to turn the body and change direction very quickly.
Which has also been suggested for other small theropods like Velociraptor or Deinonychus.
Precisely. But the musculature of the tail, along with the clawed forelimbs and reduction in teeth, make them very similar to anteaters and pangolins and aardvarks.
All of which are digging insect eaters.
Precisely. All three of these groups have long, strong tails that they use for counterbalance while walking around their back legs. Pangolins and anteaters will do this quite often, but also to brace themselves while digging.
Oh.
Kind of like we were mentioning with the marsupials, and even with those ancestral or simpler prehensile tails, that using this to brace while I stand up and dig into the termite mound, having a powerful tail is helpful for that.
Yeah, that you are doing something very strenuous and powerful with the front end, so you've got effectively 3 back limbs, kind of like with the kangaroos,
Yep.
anchoring you in position.
Yes.
Oh, interesting.
We also see a trend in tail length. The long-tailed pangolin is the longest-tailed mammal alive today, proportionate to its body.
Whoa.
Yep.
Oh, it's all coming together.
And the musculature of the pangolin tail is very similar to many features. Not all features. They made sure to note that there are many that are weird and different. But both in the muscular and skeletal structure, lots of similarities between these dinosaurs and pangolin tails.
Interesting. So that tail structure could potentially be an indicator of a similar digging lifestyle.
Yes. Diet, lifestyle, and behavior.
Wow. Very cool.
Super weird. And then, of course, theropod tails go on to get even weirder when they eventually turn into bird tails.
Yes,
like,
because birds do all sorts of stuff with their tails.
Birds have a notably reduced tail with less vertebrae and a fused end to it called the pygostyle. That is a rod-like structure that supports the main feathers of the tail and the muscles that will fan them, while the vertebrae before that, the shortened part of the tail before that, are very flexible, able to angle the tail and move it around. This is why birds are able to flap their tail and move it up and down, but also fan or bring in the feathers of the tail.
Yeah, we talked about this a bit in episode 37. Bird tails are an extremely important part of flight.
Yes.
It's a way for them to have a lot of flexibility in adjusting the flight surface of their body.
And this is something that we looked at many groups of theropods because there are many non-bird theropods with feathered tails, and some of which that also have pygostyles. Many oviraptorosaurs have shortened tails with a pygostyle at the end, sporting many feathers, and none of them are thought to be flighted.
No, they have no other obvious flight features. In fact, they have obvious not flying features.
Yes, exactly. So this tail is not just a flying tail. It is a specialized tail feather tail. It's something we see in multiple groups. There are also ones with long tails with a pygostyle for special feather attachment.
Yeah, and given what we were saying about oviraptorosaurs before, it wouldn't surprise me if that was helpful in display.
Yes.
Moving your tails around, now I'm thinking of a peacock.
Yep. And then we also have early birds that were likely flighted with long tails.
Yeah, and often they will have long tails with feathers
Yes.
that might have helped in flight.
So even the bird tail, which you would think, well, obviously that's because they're flying. No, we see that feature in non-flying groups, and we see flying groups without that feature.
Yeah, and we talked in episode 148 about gliding, that there are certain dinosaurs that aren't birds, notably Microraptor, that is thought to have possibly been using its tail, because its tail has aerodynamic feathers on it, to help in gliding.
Yes. So there are many situations where it gets diverse and may contradict the assumptions you would have thought. That, well, if we see that short bird tail, that's a flying tail.
Right. Not always.
Not always. And the list would go on and on. This is a topic that we could have shuffled all the examples we used for tail evolution and tail diversity, and it would have been just as rich of a discussion.
Yes.
There are so many we didn't even talk in detail about the different kinds of swimming tails.
No.
Like tail displays we didn't get to touch on much. There are so many other things that can be done with tails.
I didn't even get to mention the spider-tailed vipers.
I know.
But You're just going to have to Google it.
There's so many different things tails have been used for, are used for, different ways the tail have been adjusted and reshaped, and additions or reductions.
And different ways that we as scientists, and especially as paleontologists, can look at tails as indicators of how animals are living their lives.
Yeah. The reason I started the discussion by saying that tails are something we often don't think about as much as we probably should is because tails are critical to the lifestyle of an animal, whether they're there or not.
Yeah.
And it is often just as informative to look at the tail of an animal as to look at its teeth or its limbs or its anatomy internally. Like, the tail will tell you a ton about how that organism is living.
Yeah. It's a very important, very widespread body part that is so familiar that it's easy to forget just how crucial it is.
Yes. Now, at this point, we're going to wrap up the discussion on tails.
Yeah. Like we said before, if we didn't mention your favorite tail example or your favorite tail, let us know. Comment in all the places you find in the episode description.
We would be happy to revisit tails. But before we wrap up the episode completely, our last section, as usual, is our patron question. Every episode, we have a section for questions submitted by our patrons. When you sign up on Patreon at a certain level, you can submit questions that we answer here on the podcast. And what is today's question?
Today's question is a fun one. It comes from Quags, who asks, what are some quick, interesting stories from your time as science educators, particularly involving kids or questions from kids? I used to give presentations at the local children's museum, and I have some great stories and would like to hear yours.
Oh, delightful.
We have tons of stories. Let's do a couple.
Yes. So one of my favorite things that will often happen with kids, or I love it most when it does happen with kids, I guess I should say, is when they ask a question that is not only a question I haven't heard before, which is always...
Those are my favorites.
That's always fun.
New questions.
But every now and then it'll be a question that not only I've not gotten that question before, but it is a really like, I haven't thought to think about that question.
Yeah.
One of my favorites was at the aquarium, and a kid who came up to our shark teeth station and found out I was a paleontologist, came up somehow when we were talking, and they were a fossil fan. And so he immediately got more excited and asked, he started going, so you know about Megalodon? I was like, sure do. Let's talk about Megalodon. And then he went, how fast were they?
Mm-hmm.
And I had a moment of, I've never been asked that about Megalodon. I've never considered it myself about Megalodon. I don't research Megalodon, but I've never considered it. And I don't think I've ever seen a documentary. Like, I just don't hear that. I'm sure it's been studied. I'm sure it's been considered by experts. I've just never considered. This kid was the first time that perception had been brought in. So I sat there with him and speculated a bit about, okay, well, what could we tell from what we know about Megalodon and how fast it might have been? And it was great.
Yeah, I love getting questions from kids that make me think about something.
Yes.
That's happened at the museum a number of times where someone will ask a question, especially kids will ask a really odd, kind of out of left field question, and I'll go, I don't know the answer to that question, and I've never thought about it before, but that's a great question.
Yeah, give me a second to ponder that.
I was trying to think of a good example. Have I ever told my Makes You Think story on the podcast?
Oh, yeah.
I feel like maybe I've mentioned it for one of the Patron things.
Maybe.
That's one of my favorite story, but it's too long for the Patron question section. I had a question earlier today. I was giving a tour to a group of high schoolers. We were walking around the museum. We were standing in front of an exhibit, and one of the kids in the group was really excited because we had some horse fossils on display. And the teacher said, oh, she likes horses. And I started to explain some stuff about the horses. I think I was pointing and I was saying, oh, you can see that this ancient horse has multiple toes in this picture. And then the kid said, yeah, and you can sometimes see evidence of those on the foot bones. And I went, yes, that is absolutely correct. And it was super cool to have this kid contributing some of the important info. And then we just talked about horses for a little bit. And I let her chime in with some horse info because it turned out she didn't just like horses. She works with horses. Like she rides horses. And this was a kid who really knew a lot about horses. And so we got to do just for a little bit, just a tiny bit of co-educating the two of us. And I was absolutely happy to let her share some of that info for the rest of the group. It was really cool.
That's awesome.
We could sit here and swap stories from educating all day long. Stories for kids, stories with adults, stories in different contexts. If you'd like to hear more about that, please feel free to ask us for, future question things. I got to tell that Makes You Think story at some point. That's a great story.
Well, and I was going to say, a great avenue, if you are right now frustrated that you did not get to hear what makes you think, we are approaching the end of the year, which, as we already mentioned, means the end of the year Q&A is coming up.
We do this every year. We do a big, long episode that is just a mailbag episode. We answer your questions. The submission form for questions will open in mid-November. It will close in mid-December, and we will release the end of the year Q&A at the end of the year.
So that's a great place to send those kinds of follow-up questions.
Yes, and if you would like to discuss those kinds of topics, a great place to do that is on our social media, on our Facebook, or especially on our Discord.
Yeah.
You can find links to those down in the episode description. Thank you, Quags, for asking that question. That's a fun topic.
Also, just to peddle our Patreon a little bit more, we also do Patreon live streams.
Oh, we sure
every
do.
month, which we get onto conversations like this, on topics like this, very often. So if you want to actually just be able to have a chat, that is another great way. We are always open to those kinds of discussions.
Absolutely. Those are archived, by the way, so if you're a patron, you can check out those links and go rewatch the old live streams.
Yes.
And thank you to all of our patrons, as always. Thank you to our listeners. Thank you to our requesters, and thanks to you for listening.
Yes, this was a ton of fun. I had so much fun gathering the notes for this one. There's so much that had to be cut out, but the tales are awesome. Speaking of awesome content, All of the spooky episodes this year are now out.
All of our Dungeons & Dragons monsters have been evolved. Check them out. Join the conversation on Discord if you'd like. Keep your eyes out, as we said, for the end of the year Q&A stuff, and also for more episodes.
Yes, every fortnight. So 2 weeks from now, we will return with another topic.
What comes after Tails?
Oh.
What's behind Tails? Knuckles.
Footprints.
Actually, I think, usually. Footprints was a good answer, too. But we already did an episode about that.
We did already that. We have not done Echidnas.
We have not done Echidnas or Knuckles.
Yeah, no.
That's a different...
Both of those would be fun. Finger joints? Oh, I'd have so much fun with that.
Listeners, as always, you can request more episode topics for us, and we will add it to the request list. We will do those in due time, and we will thank you for requesting it when we do. I'm getting out of here.
Bye!
Thanks for listening to the Common Descent podcast. You can follow us on Facebook, Twitter, YouTube, and check our WordPress blog for pictures and links after each episode. Huge thanks to our patrons whose support helps keep this podcast running and who get access to bonus goodies on Patreon. The song you're hearing is called On the Origin of Species by Protodome, which we found at ocremix.org. Thanks again for listening. We hope you'll join us next time.